Reduction is the opposite of oxidation. Reduction is the gaining of electrons. When we gain electrons, you're going to see electrons on the reactant side. Electrons are going to be transferred from the thing oxidizing to the thing being reduced. So a sulfur atom by itself has an oxidation state of 0. Sulfur has its electron configuration, if we look at the periodic table, of 2-8-6. So with that electron configuration, it means there are 2 electrons in the first shell, 8 in the second energy shell, 6 in the valence electron shell. Now that 6 does not make it stable. How many electrons do we need in a valence shell? Well, if it's hydrogen and helium, they're the exceptions. They only want 2. Everything else wants 8. So you can see why the gain of 2 electrons will take this 6 and make it 8. So sulfur becomes an ion with a 2- charge. And if you look at the periodic table, sulfur has an oxidation state of -2. So this is where we get those oxidation states from, is how many electrons are they gaining or losing. So sulfur with an oxidation state of -2, or a sulfur 2- ion, means that it is sulfur with its 2-8-6 electron configuration. But since it gained 2, instead of being 2-8-6, now it is 2-8-8 with 8 valence electrons, making it stable. So that's a gain of 2 electrons. When things are reduced, they gain electrons. We see the electrons being gained on the reaction side, the reactant side of our chemical reaction. So what does the word redox mean? Redox is a combination of oxidation, here's the ox part, and reduction, that's the red. So it's called a redox reaction. When oxidation and reduction both take place. So an oxidation-reduction reaction is a redox reaction. Now, the most important thing here, and what you really need to get for your notes, is electrons go from the metal to the nonmetal. So the metal is always going to be the thing that oxidizes. So that's the thing that gives up its electrons. And the nonmetal is always going to be the thing that reduces. That's the thing that gains electrons. So really important part that breaks it down to make it a lot more simple for you is, if you remember, look for the metal. The metal is the thing that's going to lose electrons and oxidize. The nonmetal, things on the right-hand side of the periodic table, those are the things that are reduced and they gain electrons. So here, magnesium is a metal. Sulfur is a nonmetal. Magnesium is going to oxidize, which means magnesium loses electrons to the sulfur. You can see with their electron dot diagrams, magnesium has 2 valence electrons, sulfur 6. So if magnesium gives up 1, 2 electrons, now magnesium is just 2-8, it's satisfied and stable. Sulfur now has 8 valence electrons, it's satisfied and stable. If we did the electron dot diagram for this, it's magnesium, and then we would put for magnesium its charge. What's its charge there? If it's lost electrons, it's +2. So that means it's lost electrons being +2. I can get my plus to work here. And then sulfur, we put that in the brackets because this is ionic. So we have an ionic reaction here, is -2. Because it has gained 2 electrons. So when we do our dot diagrams, we can tell why they have those charges, because if it gains 2 electrons, it's -2, loses 2 electrons, it's +2. And we know that, and that's its oxidation state in the periodic table, but now we can actually see where that's coming from. So there is a saying, you can't have one without the other. Well, that applies here to our oxidation reduction reactions. Reduction, the gaining of electrons, can't happen without something losing electrons, which is oxidation. So there's a saying, Leo the lion says grr. In class, I have a little button I hit and the lion roars and everyone jumps out of their seats, but you're just watching it here and it doesn't do the same thing. Leo the lion says grr. What does that stand for? Well, Leo stands for lose electrons oxidation. And grr stands for if you gain electrons, that's reduction. So if you can remember Leo the lion says grr, you'll always remember the thing that loses electrons, that's oxidation. The things that gains electrons, that's reduction. So a few different rules with oxidation numbers, and everything to be successful with oxidation reduction reactions is we must know our oxidation numbers or we'll get it all wrong. Any free element in a reaction, so if you have sodium sitting all by itself, it has an oxidation number of 0. Iron in a reaction, iron plus something, oxidation state of 0. Potassium, oxidation state of 0. Lead, oxidation state of 0. Anything by itself has no charge. This is a free element. Our diatomics, H2, it's by itself, oxidation state of 0. O2 by itself, oxidation state of 0. P4, it's just phosphorus by itself, 0. Now in compounds, we have to use our periodic table and we have to add things up to make sure they add up to 0 for their charge, because molecules don't have a charge. They are neutral. So the charges have to add up to 0. You'll remember we did this a few months ago. Oxygen always has a charge of -2. It's one of those ones you have memorized. So what -2 gives me 0? +2. So one iron over here means that the iron must have an oxidation state or a charge of +2. 2 minus 2 is 0. That's how we get our oxidation states. And something like iron that has multiple oxidation numbers, we would say this is iron 2 oxide because it's the oxidation state of +2. Now we need to figure out in Fe2O3, what is iron's oxidation number? Well, if we add them up in this molecule, they all have to add up in this compound, to 0. Oxygen always has an oxidation state of -2. Well, there's 3 of them. What is 3 times -2? Well, that's -6. What -6 gives me 0? Well, that would be a +6. So how do I make iron +6? There's 2 irons. 2 times what gives me 6? That means the iron must be +3 for its oxidation number. So 2 times 3 is 6. 3 times -2, -6. So in this case, this would be iron Roman numeral 3 oxide. For polyatomic ions, it's the same thing, except we add up to the charge of the ion. In NO3 -1, the whole ion has a charge of -1. So the whole thing has to add up to that -1. We're not adding it to 0. It's an ion because it has a charge. Oxygen is always -2. You're always going to have oxygen in there, so that's going to make it easier on you. We know it's -2. So there's 3 of them. 3 times -2 is -6. What -6 gives you -1? +5. So 5 minus 6 equals -1, which means that nitrogen in this molecule, this ion, has a charge of +5. So we can figure out its oxidation number this way. So for this slide, what I'd like you to do is I'd like you to write down SO2, CO32-, Na2SO4, and NH4-2s. What I'd like you to do is hit pause and then try to figure out what are the oxidation numbers. When you've got your oxidation numbers figured out, hit play again and let's see if you're right. So oxygen is always -2. What's 2 times -2? That's -4. What -4 gives us 0? +4. So sulfur's oxidation state in SO2, sulfur dioxide, must be +4. Well, this is painful to write with. In CO3-2-, the carbonate ion, the whole thing has a charge of 2-. That means the whole thing has to equal, that's quite an equal sign, -2. Whole thing has to equal -2. Oxygen is always -2. So if oxygen is -2, what is 3 times -2? -6. What -6 gives us -2? +4. So that means carbon's oxidation state is +4. I guess I should have bought myself the Chromebook with a touchscreen. In Na2SO4, oxygen is always -2. 4 times -2 is -8. Sodium, when you look at the reference table, only has one choice for an oxidation number, is +1. There's 2 of them, so 2 times 1 is 2. So 2 plus what? -8 gives us 0. Well, it looks like that has to be a 6. 2 plus 6 would be 8, minus 8 is 0. So that means sulfur is positive 6. In NH4 2s, hydrogen, for us, I keep telling you, it's always positive 1. No other choice. Hydrogen is always positive 1. So with hydrogen being positive 1, now we look, nitrogen's got a whole lot of oxidation states. It looks like a 4, it's a 1. Nitrogen has a whole bunch of oxidation states, so we're going to wait on that one. But sulfur only has one negative oxidation state. Sulfur, when you look at it, has a bunch of positives, but only one negative. So sulfur is negative 2. So we've got what minus 2, all adds up to 0. Now I have 4 hydrogens at positive 1, so that's positive 4. But the whole thing is multiplied by 2 here. So really, when we look at that, I have to know that this is going to be, in the end, multiplied by a 2 on this side. So we need this to add up to be 2. So nitrogen must be what minus 4, what positive plus 4 gives me 1, because we want 1 times 2. So that must be a negative 3. Negative 3 plus 4 is negative 1. I'm sorry, positive 1. Negative 3 plus 4 is positive 1 times 2 is 2. 2 minus 2 is 0. So nitrogen in this case is positive 3. That's a tough one. So what needs to be memorized? In an oxidation part, or the oxidation half of the reaction, the oxidation number increases. If you're losing electrons, you're going to become more positive. So something positive 2 becomes positive 4. Something negative 2 might become 0. That number increases. Please remember that metals oxidize. It's the metal that's going to lose electrons. So look for the metal. That's the oxidizing part. Remember, Leo the lion says Gur. Leo, lose electrons, oxidation. And in order for this to happen, we have to have reduction as well. For reduction, the oxidation number decreases. If you are gaining electrons, you're going to gain negatives. So if you started out at 0, maybe now you're negative 3. If you started out at 2, maybe you're 0. That number is going to decrease and go down. Non-metals are the things that reduce. So things from the right-hand side of the periodic table. Remember, Leo the lion says Gur, gain electrons, reduction. In order for reduction to happen, oxidation must take place. The old definition of oxidation and reduction was if something gained oxygen, it oxidized. If something lost oxygen, it reduced. Chemists now know that oxidation reduction reactions happen with any kind of metal to nonmetal, or any reaction in which electrons are gained and electrons are lost. So we're looking at this, we can see that in this case, if I look at all my oxidation numbers, oxygen is always negative 2. It's not by itself. And here, oxidation is negative 2. And here, oxidation number for oxygen is the oxidation state is always, it's negative 2. Oxygen's oxidation state did not change. So the old definition really doesn't work in this case. But the new definition of if you oxidize, you lose electrons. So we look here at the oxidation half reaction. Hydrogen is a free element. That means it has an oxidation state of 0. In water, hydrogen has an oxidation state of +1. Hydrogen is always +1. And it's 2 times 1, so it has a total of +2 here. Well, hydrogen's going from 0 to +1, and it's doing that twice because there's 2 hydrogens here and 2 hydrogens here. Now to go from 0 to +1, it must mean you've lost electrons. You lost electrons and you became more positive in your oxidation number because you lost things that are negative. For the reduction half reaction, we look at carbon. If you have oxygen at -2, -2 times 2 is -4. It must mean carbon has an oxidation state of +4. That's why there's a little 4 below it. Carbon is going from +4 to, in this case, in carbon monoxide, oxygen's -2. What minus 2 gives me 0? You'd have to figure out in this reaction that carbon has a charge of +2, or an oxidation state of +2. Going from +4 to +2 means that it has gained 2 electrons. There's a gain of 2 electrons here. Now I know it's gained electrons because it gains things that are negative. And that negative, when you're gaining things that are negative, you're taking your oxidation number from +4 and you're reducing it to +2. So reduction, you're actually reducing the oxidation number. So we can see from +4 to +2, that has decreased. So that's our reduction half reaction. The fun's going to continue tomorrow with our next lesson, where you have to actually figure out and practice all these oxidation numbers to figure out which is the oxidation half reaction, how do I write it, and which is the reduction half reaction, and how do I write that. Something to look forward to.